In this video, I will be describing the enzyme mode of action. So pretend that Sally is eating a pizza. On an average pizza, different types of food are found on the pizza, such as cheese, bread, and pepperoni, for example. All of these food types contain lipids, carbohydrates, and proteins. However, the human body cannot just simply digest these complex molecules without the help of other proteins called enzymes. Specifically, I'll be talking about proteins and carbohydrates, since lipids are not polymeric, meaning they can't be broken down into simpler monomers. Let's get into why enzymes are even important in the first place. First, the y-axis describes energy. The higher the energy on the y-axis, the more energy is required. Meanwhile, on the x-axis, the progress of reaction is described. When a dotted line is placed on the graph, the energy on the y-axis above the dotted line describes energy absorbed, while the energy below the line describes energy released. When drawing a line describing the activation energy without an enzyme being used, it is noticeable that the reaction would require way more energy than the second line, which has a lower activation energy, meaning that the reaction will not require as much energy. That is why enzymes are important, so that energy is not used as rapidly to digest certain foods or do simple everyday things that our body requires us to do. Now, the lock and key model, proposed by Emil Fischer, is a concept where our biological systems and enzymes emulate how normal lock and key works on a door. In this case, the lock is the enzyme and the key is the substrate. The enzyme also has something called an active site, where the substrate would enter for further activity. Then an enzyme product complex is created, where the substrate becomes broken down into less complex versions of the previous molecule to become the product. One example is when proteins become a substrate and the enzyme is pepsin. Pepsin is the enzyme that catalyzes the digestion of dietary proteins into smaller peptides, serving as an essential enzyme in the early stage of protein digestion in the stomach. The induced fit model by Daniel Koshland suggested that the substrate changes conformation when in contact with the enzyme in order to achieve the desired product. Once again, we have an enzyme and a substrate, and an active site where the substrate would enter and change conformation. An example using the induced fit model can be done with starch and amylase. Starch is the substrate, and amylase is the enzyme. As starch enters the active site, the conformation of starch changes where glucose comes out of the enzyme product complex as glucose, which is then later used for energy and cellular respiration. This is useful because cellular respiration requires glucose, and starch would not be able to be used in its current form. Some key takeaways from this video are the following. Why are enzymes used? This is to lower the activation energy and increase the rate of reaction in a sufficient way. Then, I talked about the lock and key model, which uses a substrate that fits into the enzyme, creates an enzyme-substrate complex, then releases smaller, less complex molecules for the products. The induced fit model uses substrate that binds to enzymes. This causes a dynamic conformational change, which in turn creates an enzyme-substrate complex. This releases smaller, less complex molecules for the products. These are the references I used for the creation of this video. Thank you for watching this demonstrational video on enzymes and their mode of action.